Hello everyone and welcome to an OpenGL video. It's been a long time since we've done just a video rather than a stream. Today we're going to be doing a little bit of a recap of the first 29 videos in the OpenGL series. So essentially what I'll be doing is I'm just going to be going through the main.cpp file. We'll go through the functionality of pretty much everything. We'll go into the functions, and you'll notice that I have uploaded documentation. Documentation. I put more comments for all the functions, and I've also cleaned up just a couple of lines here and there. So that's all on the latest commit, or the latest 2 commits on GitHub. So those should be present on the in the repository. So let's go ahead and get started. So in the main.cpp file, we have a bunch of includes, has some global variables, and let me start out by constructing the scene. So in constructing the scene, we essentially pass in a couple of values for the GLFW version, and then the window dimensions, title, and color. And then we just set those values in the constructor. And then after that, we are going to actually initialize the scene. And what initializing the scene does is it starts up the GLFW context. So we just, by calling GLFW init, and then we set the version of GLFW, which for us I believe is 3.3. And then we just set the profile. If we have add some compatibility for Apple, and then we actually create the window. So if the window is not created, if the window is equal to null, then we just return false, and the scene was not successfully initialized. Then we load up GLAD, which is a library that provides us with our OpenGL constants and functions. So the GL key H or whatever, all those enums and all the functions, pretty much all the other stuff here that doesn't say GLFW, we get that from GLAD. And once again, if that was not initialized, then we simply return false. Next, we go ahead and set up the screen and the callbacks. So the GL viewport, so we just set the width and height initial, and then for our frame buffer size callback, we have a static method in the scene, and then for the key pressed, the cursor moved, mouse button pressed, and the mouse scroll, we have static callbacks in the keyboard and mouse classes for those. We did that around video 10, I believe, with advanced I/O, 10 or 11, I forgot which one it was. And then we set our rendering parameters. So we just enable depth test, which tells OpenGL not to show vertices that are invisible to the camera. So something like the back of an object, and that's the reason why we get this kind of depth perception. And then we finally disable the cursor. So that's why you don't see a cursor anymore. We just have it kind of like an FPS game where when you move the mouse, you're moving the camera and you don't see a cursor. And then after that, we initialize the awk tree. So initializing the awk tree simply just sets the current region to whatever we pass in, which for us is just -16 to 16 in all dimensions. All right, back into main.cpp. The next thing we do is we set up the camera, and in the scene, we devised a way to pass in a reference to a camera, so that in the scene we have a list of pointers to cameras. So scene.cameras is a vector of pointers to cameras. And then we set the active camera, so the index there, that's just the index of the list with that camera's active. Next we do our shaders. So in this method, we simply call the constructor, which I'll load it up right here, shader.cpp. What it does is it simply just generates a shader program using a vertex shader path and a fragment shader path. So we go ahead and call compile shader, which is another method we wrote, and what that does is it takes the text from a file. So in our assets folder, we have the .fs and .vs files. So those are our fragment and vertex shaders, and then it simply compiles the shaders, and then it will link the two shaders together, or it will attach the shaders to a program that has an ID, and then we will link the program to OpenGL. We'll get the errors, if any, and then we'll delete the shaders at the end because they are already linked, and then that is generating the shaders. Next, we're going to do the models. So we're going to be registering the models, and what registering the models does is we simply insert a reference to the model into our model trie. So in the scene class, we have a trie of models. If you don't know what a trie is, it's somewhat like a tree, except you can have n number of children. So for us, we have like I forget what it is, but I made a video on the trie. Go watch that if you're interested there. So yeah, we just insert the model into the trie, and each model has its own ID that we kind of use to locate the model in the trie. So the trie maps, it's somewhat like a map, but it's just a little more optimized search structure, and it maps an ID to a model pointer. Okay, now for loading the model data, this is somewhat of the meat here. So we call scene.load models, and what it does is it traverses through the model trie, and it goes through each model, and then it initializes each of the models. So in the model class, this is a virtual method because the model class is meant to be overridden. It's meant to be inherited from. So we want this method to actually be overridden because it could come from an object file. It could come from vertex data, like in our cube. In our cube, we simply pass in vertex data from here. In other things, we simply load a model from a path. But in both cases, all we do is we get vertex data from either code or an object file. And in an object file, with an object file, we're going to use the library async. So let me just pull this up. When we go load a model, we use async to actually read the file, and then we'll process the nodes, the meshes, all that stuff over there. And then for each of the for each of the meshes, so each model is made up of either one or several different meshes, and those are the different components. Like with a body, what you could have is the body is the model, but a mesh could be an arm. Or with a gun, the gun would be the model, and then the mesh could be the different components, so the scope, grip, whatever. And you can manipulate each mesh individually, so that makes it pretty cool. So all we're doing is, if we pass in vertex data like we do in a cube, we're going to call or in both cases, we're going to convert data either through this array or an object file into a list of vertices, which we have in a structure. So our vertex structure has position, normal, vector, texture coordinate, and we convert it into a list of vertices. And then we also get a list of indices, and that will be like the in order index of vertices to draw. So if the index list is 1, 4, 5, you first go to the vertex at index 1, then 4, then 5, and you draw it in that order. And that's how OpenGL actually draws it. Next, we're going to actually process each mesh. So in mesh.cpp, in the constructor, or not in the constructor, we're going to say in load data, what we're going to do is we're going to create a vertex array object. So a vertex array object, or a VAO, is essentially a pointer to a group of buffers. And in this version of OpenGL, or in older versions of OpenGL, this didn't exist. So you had to bind each buffer separately. But with the VAO in this version of OpenGL, what you can do is this VAO, when bound, you can generate other buffers, and that VAO will always point to those buffers. So when you bind it to draw, OpenGL knows exactly what data to look at. So in the VAO, when we bind the VAO, we generate the element buffer object, which stores the index list. Then we generate the vertex buffer object, which stores the vertex data, so that list of vertices. And then we set the data. We have a class for this, which in glmemory.hppp. And then next we set the vertex attribute pointers. So this essentially tells OpenGL how to process the VBO data. So the vertex buffer object, it needs guidance. So in our shader programs, in the vertex shader, you'll see we have some layout variables, and this layout isn't just random. It doesn't just do this automatically. We tell OpenGL that in location 0, in index 0, it's the position, and it's a vector, in a 3D vector. In location 1, 3D vector, normal. Then location 2, it's a 2D vector for the texture coordinate. And we set all that right here with a couple of parameters. And then we cleared the buffer object and the array object. So once again, when this VAO is bound, it will know to look at what data. So when the VAO is bound, we set the data right here, and then we give it the attribute pointers. So the attribute pointers give us a location of where the data is and how to actually go through the data. And then after this, we're going to process the textures in if we had a textured cube or something, we would use our texture class, and we would just create them manually. But with async, there's a method that we have which is called load textures, and it essentially just takes the texture or the texture paths from the object file, which point to other files that were downloaded with the object file, and it just loads those in and puts them with the model. Alright, now back to main.cpp. After we have loaded the models, so we've loaded the data, we're now ready to generate our initial instances. So our model instance system, we did this, it was a rather confusing video, I'd say, so I'm going to clear up some of it right now. Essentially, we have models, and then we're going to have multiple instances of those models. So you can have, let's say, 10 spheres, and that's actually what our maximum is. So the model has instances that it points to, and the way to actually generate an instance is to call scene.generateInstance. And what scene.generateInstance does is it gets the specified model and generates an instance there. We first determine if there's space, and then we generate a new rigid body using the size, the mass, and the position of what we pass in, and then we also pass in the ID of the model, because the rigid body, we want to know what model it is, so that in the future we could possibly figure out how to react to collisions based on what type of model it is. And then back in scene.cpp, what we do is we generate a new and unique ID using this generate ID method, which sequentially generates lettered IDs for the instances. Then we have we set the instance ID, and then we insert this instance into an instances trie. So the scene has two tries, the model trie and the instance trie. The model trie once again maps the model IDs to models, and the instances trie does the exact same thing. But it maps the instance ID to a rigid body pointer. And then after this, we add the instance to the octree. And what add to pending does is it, since our octree takes bounding regions as its objects, what it will do is, since the rigid body has a pointer or has a model ID, what this method will do is it will get all of the bounding regions of the model that the instance is an instance of, and it will just take all those bounding regions, transform them to match the current instance, and then push that to the pending queue. And then after we generate our instances, we're going to go into lighting. So there's 3 types of light that we have, and we have a different structure for each light. So we have directional light, which is like the sun, and what that is it just generates parallel rays that all come in at the same direction, same strength, wherever you are, so like the sun. Then there's a point light, so like a light bulb, which is just pretty much a point light, and it emits light in all directions. The math is a little more complicated because you have the strength decreases as you go further away. And then there's a spotlight, so something like a flashlight, it now has a position and a direction. So it only points light in a certain direction, and you have cutoffs and also constants to determine how bright it is at different levels. So as you go further away, the strength decreases of the light. Now, after the lighting and the generating instances kind of fall in the same category, because for our lamps, we actually generate an instance for the lamp, and then we also set up the lighting. So after that, we go ahead and actually instantiate the instances. So what does this mean? Haven't we already set up the rigid bodies? Well, yes, we have, but there's another part to it, because there's a trick that we can do, and it's called instancing, and that's kind of where the instance name came from. But you can draw multiple models of or multiple instances of a single model with a single call to the GPU. So if we had an array of models, rather, and we called the GPU several different times, that would be slower than calling it one time, but just setting the data each time. So for initializing the instances, we have to generate another VBO for the positions and the sizes. And depending on what the model is, there are different switches. It might be dynamic, could be static, but for something like a moving object, it's going to be dynamic draw. We're going to use GL dynamic draw because the instances will not be constant. And then we just set the VBO data, and it could be null if there are no instances present yet. So that's where the maximum number of instances comes in. So it just has a null pointer. And then we set the attribute pointer. So once again, we bind the VAO for each mesh first, and then we actually set the attribute pointer for each VBO. So for the position and size VBO, we set them separately for each mesh. Okay, so that's how we initialize the or one more thing, just because you might be wondering why I didn't generate the VBOs down here when the VAO is bound. It doesn't really matter, because even if we don't generate it when the VAO is bound, the pointers, the VBOs have pointers to data, and as long as these attribute pointers know what VBO it's looking at, it will point to that same set of data. So that's how that's going to work. Okay, now last thing before we get into the main loop, the prepare. So scene.prepare. What this does is it simply updates the octree. So what that does is in octree.update, since the tree is not built and the tree is not ready, it's going to go ahead and process the pending results. So the queue may have stuff in it, so those instances that we already instantiated, they will be in the pending queue. So what it will do is it will go through each queue, determine if it fits in the octree, and then it will add or insert the objects, or put them in the object list. Yeah, so it just puts all the objects in the root, in the root node of the octree, and then it builds the octree. And what that does is there's a couple of rules. So it'll subdivide cells until there's one object remaining, or the minimum dimensions have been met, and then it will insert objects into child cells if and only if it fits completely. I made a whole four videos on the octree. Go watch those if you want a refresher on what an octree is. Okay, now we are into the meat of it, the main loop. So this is what happens. This iterates 60 times per second or whatever, and that's your frames per second. So first thing we do is we calculate DT. So that's just the time between this frame and last frame. Then we update the scene. So updating the scene, all it does is it clears the color. So it just sets the background color of the of the window, and then clears the bits that have been occupied for drawing. So for the GL depth buffer bit, that's just GL depth with the scene.setup. We depth test. This bit is being used, so we're just clearing it for the next draw, and then the color as well, because it's using colors. So that's update. And then for process input, that's just a method here we call scene.processInput, which just determines which changes, I'll say, the mouse, or it determines if the camera should be moved. It'll move the camera if there's keyboard input, or if there's mouse input, something like that. And then after that, it will do the specific inputs for the program. So the keybinds, like the escape key, setting the window to close or something like that. Now the other functions that you might see in the middle of the loop are mark for deletion. So right here, if a launch object is too far away, we want to mark it for deletion. All this does is it just activates the kill switch. I'm going to use that word. It activates the kill switch on the instance. The instance has a combination of switches, and the dead instance dead is one of those. And then it also pushes it to a list of instances to delete. And then you might also see render, so render shader, and what this does is it just takes the shader and puts the camera values first, and then the lighting if we want it. So this will allow us to create that kind of 3D environment and where you can move around in. And then also you might see render instances. So this will render the instances of a specific model that we tell it to, using that shader that we just compiled. And all this will do is it will call models.render, and what that will do is it will either if the instances are changing, we're going to update that VBO data for the positions and sizes, and rotation will come in after. And then after that, here, let me just it just updates the VBO data for the positions and sizes only, and then we render each mesh, and mesh render. All that does is it either sets the material values or the textures based on what it wants, and then it draws it using the VAO, which is a method we wrote, and that calls GL draw elements instanced, which uses instancing. So you make one call to the GPU to draw the elements, and that's the only call you make to GPU to draw something for this model. All right, so that's that. Now for at the end of the loop, you're going to see new frame and clear dead instances. So for new frame, we have the octree, two octree methods. First one is process pending. When the tree is built, it will simply just go through the pending queue, and if there are elements in there, it will insert the object if it fits. Otherwise, it will put it to the back. Back in scene.cpp, and then it calls octree.update. So we already called this method once, but that was to insert the pending objects. So for update this time, what it's going to do is it's actually going to show us the full glory of the octree itself. So we're going to, what it will do is it will remove the dead branches in the objects. So for the branches, if the lifespan has reached 0, and then for the objects, if the kill switch has been activated. So that's what marking for deletion actually meant, and it would then kill the object or just remove it from whatever, from the octree. And then it then checks to see what the moved objects are, and if objects have moved, it will relocate the object because it may have moved cells. And the way to do that is it moves it up through its parents until it fits, and it starts in the current one, so it could stay in the current cell it's in, and in that case it wouldn't move. And then after that it moves it down as far as possible. So in any case it could just stay in the current cell, but then so it shoves it down as far as possible. And then after that we check for collisions, which is the most exciting part of this. And we first start with the current cell, and then we go to the children, and then we go to the parents. So this collision algorithm was written in bounds.hpp, or bounds in the bounds classes, or in the bounding region class. That's it. All right, now back into scene.cpp. After it's gone through the octree, we then swap the buffers. So we just swap the frames because OpenGL generates the next frame. So it will generate one frame, but so in the first frame it generates it, and then it generates a second frame, then it displays the first frame, and then as it's displaying the first frame, it generates a second frame, and then swaps them at the end and starts a third frame, and so on and so forth. And then it pulls events. So what this does is it just it just gets all the new input, so any events that have occurred. So you'll have it's just event processing. Okay, so that is the main loop, and then outside of the, or next method, sorry, last line in the main loop is to clear dead instances. All that does is it just removes all the instances that have been marked for deletion, and since they have been marked for deletion, they have been added to the instances to delete list. Now, outside of the main loop, once everything is done, we're just going to simply clean up the scene. Now, cleaning up the scene, there's a couple things here. So first is we clean up all the models. Now, cleaning up all the models, what that entails is it goes ahead and cleans up all of the VAOs, so the vertex array objects. It just clears all the arrays there, frees up the memory. We also cleared the VBOs for the model, and then where is it? Then it goes through the model, the tries for the models and the instances, and it destroys that, so it frees up all the pointers. And then we destroyed the awk tree, so that just frees up the pointers and the memory as well. And then finally, we terminate the GLFW context, and that is episodes 1 through 29. So I'll just run it just to show you guys what we have so far. And so you see your awk tree, we have our 4 lamps, and then our launch objects are pretty small. I'll just make this full screen so you guys can see it. So it's like that, and then if I press F, it launches an object like so, like that, and it's pretty cool. So in the future, we are in a very, very good spot. There's a mosquito, hold on. Yeah, we're in a very good spot. We have pretty much set up a framework that will allow us to expand very quickly. With rotation, we simply just add another VBO for rotation on top of the positions and sizes, because that's all involved in the shader transformations. And then for collisions, we have the react to collisions, I believe, in the rigid body. Where was it? Let me go to awk tree. Can I find it? I don't know if awk tree is open. Here it is. So when we go ahead and check for collisions, it just prints it out, but we use the algorithms, and then we can interact with them. So when we print out, we can replace this with rigid body dot bounce off of, something like that, or reverse the velocity, reflect the velocity. Stop the object. We can do whatever we want, but we have created a framework that will allow us to expand, scale up. That's a term, scalability. But we will be able to incorporate a lot more functionality very soon, and I am looking forward to that. So that is just a quick recap. I think that's been about half an hour. Damn, that's kind of long. But anyway, hope you guys enjoyed. Hope this cleared up some things if you guys were a little iffy. If you need any more help, leave a comment. I'll respond. Hit me up in the DMs. I don't really care. Don't send me any illicit pictures though, because then I will not respond. Although I might reply with one of my own, but I don't know. All right, so I will post this video probably tomorrow, which will be Thursday. I don't know, but yeah, you'll see this up then. Hopefully it gets 1 million views, and then we'll be able to go from there. So hope you guys enjoyed, and I will see you in the next OpenGL stream, which may be next week, but I need to figure out a couple of things until then. I will see you guys later.